Okay, so we finished the example on free fall last time. The theory for free fall is just this one-dimensional constant acceleration motion we discussed. So what we usually do is that if you call the vertical direction, vertical axis, y-axis, usually we replace all the subscripts x with y's, okay? But that's the same theory, right? You use the same theory in free fall because it's a constant acceleration motion. So a few things I want to emphasize based on the question I usually get in this part, okay? That's the last slide. I summarized them on the last slide. Zero reference point. You always need to pick a zero reference point, right, when you plug numbers in. In y direction, in vertical direction, there are two zero reference points we usually pick, okay? Sometimes we pick the starting point of the motion, okay? Sometimes we pick the ground, okay? But once you have chosen a zero rest point, okay, you're gonna use then you want to find the height of this ending point, okay, relative to that zero reference point you pick, okay? So you're gonna make sure you get the directions right, you get the signs right, okay? If I pick a zero reference here, okay, that's a starting point of motion. If this is my y equals 0, right, that's a zero height I pick. This guy is gonna have like say 5 meters, right, because it's higher than zero reference. And if I pick a point like here, that guy must have negative 3 meters, right? You can't get a positive number, or if you want to plug in the height of this point in those equations, okay, after you have picked this as your zero reference point, okay? Anything lower than the zero reference point is going to have a negative value, okay? Negative height. Don't be afraid of negative height. Height is totally relative, right? It totally depends on where the zero reference is, right? You can pick any point as your zero reference. It doesn't have to be always the ground, right? And then we can have things lower than the ground, right? If you go to an elevator, sometimes you see a -1 floor. Are you going to freak out? This doesn't make any sense for me. I'm scared. No, -1 means it's the basement. It's 1 floor lower than the ground floor, right? So the negative signs, they're telling you something. They're telling you something, okay? Don't freak out when you see negative numbers in physics, or you need to assign negative signs for some numbers in physics, okay? And then initial and final points from the problem we just solved. You can pick any points as your initial and final points, and then apply the 3 kinematic equations, right? You can even change the initial and final points, okay, when you solve different parts of a problem, right? It also depends on what you're solving in that part. And then the initial and final points, they don't have to be always the very beginning of the motion, the very end of the motion, right? You can pick any points between these 2 points as the initial and final, and then use the theory to find things you need, okay? You have a lot of freedom, okay, picking these points, zero reference, initial and final points. And G value, okay, this is another question I usually get in this part. A lot of people, they always ask me, is the G negative 9 point A? Okay, why do we always plug negative 9 point A when we solve a problem in free fall? G is a symbol for 9 point A. Because 9.8 meters per second squared, that's a free fall acceleration on the surface of the Earth. It's a constant, okay? Any constant in physics, we use a symbol to represent them. So we don't need to write this number and the unit every time. We use the symbol so everyone knows what we mean. I usually use the pi, okay, as an example for people to understand all these other constants. Pi is the ratio between the area and the square of the radius of a circle, right? And we know the number is 3.1415926. But if everyone agrees that, let's give it a name. It's such an important constant in nature, in math. Let's call it pi, Okay, so every time I say pi, you know what I mean is that number. I can even use this symbol if I want to get some expression, right? Using the ratio between the area of a circle and the radius squared. Okay, there are a lot of equations in physics have pi in it. Okay, so this little g is a name we give to this constant free fall acceleration on the surface of the Earth, 9.8 meters per second squared. So we don't need to write down 9.8 meters per second squared every time we talk about this free fall acceleration. We can just say, oh, little g. Okay? We never make little g negative. It's a constant in physics. We don't make constant negative in physics, right? Some books, okay, you may have read some books which has this notation. They would write little g negative 9.8 meters per second. This is confusing. I don't like this notation. This is a very bad notation. This is really bad, okay? Little g is a constant, okay? You shouldn't call it negative, okay? But why do we plug in negative 9.8? Because we assume when we draw a coordinate system this way, we are assuming we always need to set up coordinate system when we study the motion of anything, like in 2 dimensions, okay? When I draw a coordinate system, I need to define positive and negative. I need to define positive x and negative x, positive y and negative y, right? 99% of people will draw a coordinate system this way, right? This is again just convention, okay? There's nothing wrong if you want to draw x this way and then y this way. Nothing wrong, okay? But if you use this coordinate system, you're assuming right is positive, right? If something has an acceleration in that direction, you would say ax equals negative 3 meters per second squared, right? If something moving in this direction, you would say it has an acceleration 2 meters per second squared, positive. Or something has a velocity in this way, you would say the velocity is 10 meters per second in positive direction. Or something's moving to the left, I'm going to assign a negative sign. So you see that based on the signs, I know the direction of these vectors. I don't need to write the words. It's the same deal in y direction. Now, if anything up is positive, then anything down must be negative. And free fall is a very special constant acceleration motion in nature, right? The acceleration is always down because gravity is always down, okay? So free fall, if I want to use these equations, what is the acceleration I plug in? Negative 9.8. Why? Because the acceleration is always down, right? It's not up, okay? So for free fall, the acceleration I plug in, if I need the value, I would do this, right? Negative 9.8. I'm not making little g negative. I never do that, right? Little g is the name for this. Pi is a name for this, right? Do you ever make pi negative, right? Do you ever say that, oh, if you want me to plug in pi, I'm going to do negative 3. No, you don't, right? You don't, okay? It's a name for that. And sometimes we don't want to calculate numbers. We want to get expression, right? We want to, like the time, falling time we derived last time. So I want to plug in a symbol. In that case, you see that I'm going to replace 9.8 with its name, with its symbol, right? Again, I'm not making little g negative. Okay, little g is still 9.8 if I want to plug numbers in at the end. I'm assigning a negative sign because think of this is just 9.8. G just equals 9.8. There's no difference between them, right? I'm assigning a negative sign because this thing is down. The acceleration is down, right? I have to assign a negative sign so that it's different from a positive direction, okay? This negative sign is not because I'm making little g negative. I never make little g negative. I never make pi negative, right? We don't do that. It's because when you draw a coordinate system, you use these equations. You're working with vectors. You need to distinguish left and right, up and down. We use signs, okay, instead of words, okay, to plug in and then do the algebra, okay. So everything is clear, okay. The signs at the end, the signs are also going to tell you the direction, okay, and the magnitude of any vector, okay? All right, so that's that. Now we're going to move on to the next PowerPoint, PowerPoint 4. We have discussed one-dimensional motion, right? Now we're going to move on to two dimensions, okay? So the two-dimensional motion, it's a little bit more complicated, right? Because now you're dealing with like things moving not just in x or y direction, in both of them, okay? So the two-dimensional motion we want to discuss in detail is this projectile motion, okay? Because we have a very good theory for projectile motion, okay? What is a projectile motion? As I said, if you throw something, right, the object is going to move in a parabola. So it doesn't matter how you throw it, right? Horizontal or with an angle. It always moves in a parabola. It doesn't move in a straight line, right? So it looks more difficult than one-dimensional motion. In one-dimensional motion, things always move in a straight line. But the theory is this, okay? If you break the motion, right, we have learned that in vector analysis, right? So when you work with vectors, okay, it's always easier to work with their components. So if you break the motion, a projectile motion, into x and y directions, you also get the two components, the motion in x direction, the motion in y direction. And it turns out that two motions in x and y direction, they are the motions we already know. Okay, they are the motions we already know. In y direction, it's just free fall. Why? Because when you throw something, okay, after they leave our hands, there's still only gravity on it. If only gravity is on it, it's free fall. It only has one acceleration down, 9.8, always. Okay? So if you throw something, okay, and this is not intuitive at all, right? So I've emphasized this many times, okay? If you study nature, you don't trust your intuition, okay? You don't trust it. Our intuition has a lot of limitations, okay? You have to use a theory, a law, and then do math. Math helps us go way beyond our senses, okay? So if you break it into x and y, you can realize that in y direction, it's still free fall. If you compare only the motion, the y component of the motion, of a projectile motion to a free fall, you can find out they're exactly the same. Exactly the same, okay? So here's a image on this slide 2. You can compare that. So the simplest way you can compare is that you compare a horizontal projectile motion and a free fall with no initial velocity, right? So if I throw something this way, okay, so you can plot the trajectory of this object, right? And then if you compare it with something falling straight, okay, only under gravity, you can actually find out if you measure their location and their velocity only in y direction, okay, at every second, you're going to find they are exactly the same, okay? So this horizontal motion, okay, in y direction, so for every second, the velocity, the change in the velocity is always 9.8 meters per second squared. And then the distance is always you can calculate it based on the theory. So you compare the motion, the y component of this motion with something in free fall starting from this point. In y direction, all the information is going to be the same. All the information is going to be the same. So in y direction, it's still free fall, okay? It's still free fall. And in x direction, okay, it's going to be the same as a uniform motion. So if you compare the motion in x direction with something moving, starting from this point, moving horizontal with a constant velocity, at every second you compare them, they will always have the same velocity, cover the same distance. Again, take a look at an image on slide 2 and slide 3. Okay, so in x direction, you break it, you get a uniform motion, so no acceleration. And if you think about it, which makes sense, because gravity is only in y direction. If you throw something, there's nothing on it in x direction. If there's nothing on it, it feels like it's as if it's moving without any force or any impact on it in x direction. Okay, so of course it's going to move just with the constant velocity, and that's inertia we're going to talk about when we study Newton's laws. Okay, so and then you can do experiments to test a theory, right? If I tell you a theory, you don't believe that, I can tell you how to do an experiment, right? So all you need to do is that, for example, if you want to compare it with free fall, okay, so you can set up a very nice experiment. You have a device here. This device is going to launch something in free fall and horizontal projectile motion at the same time. And then if you can plot their motion at every time, you can take a slow motion video, okay? And then you can compare them frame by frame. You can find out they're always going to reach the same height at the same time, okay? So I attach a link to a YouTube video of this experiment, okay? You can take a look at it. So if you have the two balls, okay, and you launch them, one in free fall, no initial velocity, one in horizontal projectile motion, and then you compare them, their location in y direction, frame by frame, it's always the same, okay? In y direction, it is free fall indeed, okay? And in the x direction, you can also do that, right? So you can actually, again, you can take a video of a projectile motion, okay? And then you can actually measure the distance of this ball, of this projectile, okay, in x direction, and compare them frame by frame. You can actually find that the distance it covers in each frame, the same amount of time, it's going to be the same. So that's how I verify this theory. Right? Okay, so the key is this. When you study projectile motion or any two-dimensional motion, you break it into x and y components, okay? And then you just work in x and y directions independently, separately. They're totally independent from each other, okay? And then in a projectile motion, we already know these two motions, okay, very well. In x direction, right? The acceleration is going to be 0 in the projectile motion because there's nothing on it, it's just moving on its own. In y direction, acceleration is negative 9.8, or if you want to use the symbol, it's going to be negative g. Okay? And these two motions, we already know how to work with them. This is the simplest one, right? It's just like distance equals velocity times time. And then this equation, you can use the kinematic equations. Okay, so for all of, and this zero acceleration is also constant acceleration. So for constant acceleration, you can always use this theory. So if you want to study horizontal motion, projectile motion, you still use the theory, the kinematic equations we learned earlier. You don't need a new theory. You just need to apply this theory in x and y direction separately. Okay, you don't get them mixed up. Okay. So let's take a look at the slide 4, okay? So in this graph, you can see the velocity, okay? So there are arrows on this graph showing the velocity, the total velocity of this projectile motion, and the x and y components of this velocity, okay? So it's very nice. You can take a look at this whole trip. And then this blue arrow is the total velocity of this. This is a football, okay? Of this football when it's kicked. You see the blue arrow is the velocity of this total velocity of this object, and it changes all the time, right? It changes all the time, both magnitude and the direction. Okay. But if you break it into x and y direction, right? So the x direction is all these red arrows. You take a look at these red arrows. In x direction, constant. Always in the same direction, the same length, right? So in x direction is a uniform motion, right? In y direction, it's free fall with an initial velocity. So it's pretty much like you throw something up, right? Take a look at the green arrows. That's the velocity of this football only in y direction. So it gets shorter and shorter, shorter on the way up because the velocity in y direction gets smaller, smaller, and smaller until it reaches top. There's no velocity in y direction. But it still has velocity in x direction, right? Because it's still moving in x direction. And then it's going to turn around at the top in y direction. It's going to start to fall, okay, in y direction. So the green arrows, you can see that now the direction is reversed. The green arrows are going to get longer and longer and longer because now it's falling, gravity is pulling it down, it's going to get faster and faster in y direction, okay? If you break it into x and y components, okay, it's very clear they're just uniform motion and free fall, okay? So we're just going to still use the same theory we learned, okay? The kinematic equations to study projectile motion, okay? So you should always be careful. This is the, some people make mistakes in this part because they always get these values mixed up, okay? You don't use any x values in y direction. You don't use any y values in x direction. That's a very common mistake people make in this part, okay? So you should be very careful. The only value you can use in both in x and y direction is the time. Okay, because the time is the same, right? It's moving both in x and y direction. Of course, the travel time is going to be the same in both x and y. Okay, that's the only thing you can plug in both directions, the same value. But other than that, velocity, x and y direction, totally different. Acceleration, totally different. And we already know the acceleration in x and y directions in the projectile motion. You don't even need the problem to tell you the acceleration of this projectile motion in x and y, right? You already know that. X direction, no acceleration because there's no force, nothing on it, right? Y direction is free fall, so it's always 9.8 down, okay? So you see that all these values, they're different in x and y directions. You don't get them mixed up, okay? The only value you can use in both directions, the same value, it's gonna be the time, okay? So of course we're going to practice this theory again in projectile motion because it's going to be a little bit more work, okay? And 2 dimensions is always more complicated than 1 dimension, okay? But first of all, let's take a look at the conceptual question on the next slide, okay? So I want to use this to help you test your understanding on the projectile motion we just discussed. Why an object is thrown horizontally with negligible air resistance? Okay, which one is the right answer? So how does the horizontal speed change? How does the vertical speed change, right? Horizontal motion is this, right? You throw something with a horizontal initial velocity. I know the motion of this guy is going to be like this, right? So I want you to tell me how the speed changes in each direction, horizontal direction and vertical direction, okay? Which one is the right answer? Okay, if you understand what we just said about projectile motion, in horizontal direction, how does the speed change? No change. Acceleration is 0, nothing is in x direction on it, right? So in x direction, if you want to draw the velocity, it's always the same. That's going to be Vx, right? So the speed doesn't change in x direction. The horizontal speed remains constant, right? What about the vertical speed? It's a free fall. The speed gets larger and larger. The speed is always down, but it gets larger and larger, right? This, no speed. This, a little bit. Now it's going to be a little bit larger. Now it's going to be even larger, okay? That's Vy. Okay, you break it and it's going to be these two motions we already know. Uniform motion, constant velocity in x direction, and free fall, constant acceleration motion with 9.8 in y direction. Okay, so A is the right answer. The horizontal speed remains constant, but the vertical speed increases, right? That's going to get faster and faster in y direction if it's thrown horizontally. All right, so that is this. Now let's take a look at a real problem. Okay, we're going to use some numbers to, again, practice this theory. okay, in projectile motion. Okay, we're gonna use Michael Jordan's iconic dunk from the free throw line, okay, as a real life example to practice this theory in projectile motion. Again, Michael Jordan is always the greatest of all time, no question. So if you haven't seen that, okay, that's the slam dunk contest in 1987. Again, I think it's before you were born, okay. So he became the champion, of course, okay, at the end. So the dunk he made, okay, one of the dunks he made, it was from the free throw line. If you haven't seen that, okay, your life is incomplete, okay. Please use the link, okay. Use the link I attached on this slide, and then take a look at the dunk he made, okay, from a free throw line, okay. That was beautiful, really beautiful, okay. Now we want to use these numbers, okay. So it was recorded that he had 0.92 seconds of pure hand time. So he was in the air for almost a second. That's amazing, okay. And the distance from the free throw lines to the baseline is 19 feet, okay? So that's one of the numbers for the basketball court. I want to estimate his takeoff velocity, okay? So let's first draw it out. So when he's in the air, there's nothing on it except gravity. So he's in projectile motion when in the air, okay? So if you have watched the video, okay, so say this is a free throw line, okay, this is the baseline, okay, and then this is the hoop. See, okay, let's see. Let's just make the baseline here. All right, so, and then his pass is like this, something like this, right? He's gonna take off, reach the top before the hoop, and then if you watch it carefully, he's already moving down, okay, when he dunks. And then he's gonna land about the baseline, okay? So we're gonna approximate this as a totally symmetric projectile motion. He takes off at the same from the floor, and then he's going to land on the floor on the other side, right? Okay. We're going to also ignore his size. Okay. We're going to treat it as a point mass. Okay, to make things simple. Okay. Because we just want to estimate his takeoff velocity. So what is his takeoff velocity? Well, if you draw it, it's going to be a vector, right? So it's going to be vector in that direction. So then you cannot find it directly, right? Whenever you work with vectors, you should be extremely careful. You can't find them directly. You would have to break it into x and y direction so that you find x and y components. Then you combine x and y components using trick. You can find the magnitude and direction. So that's what we're going to do here, right? So I'm going to first break it into x and y components, right? So this is Vxi, and then this is Vyi. Okay? I know that at the end I want to find this Vi, both the magnitude and the direction. But once I find these two components, I can combine them, find this. And how do I find the components? You see that? That's when you use these theories. I do have Vxi and Vyi in this theory, okay? So I can find Vxi in x direction, find Vyi in y direction, okay? So that's what we want to do here. The first part, find x component of his takeoff velocity, okay? So that's the Vxi. And x direction is easier than y direction because we know that in x direction it's a uniform motion, right? In x direction, the velocity is constant, right? It's always constant. So if I want to find Vx, I take a look at these three equations. Which equation do I use? Well, actually, every equation has Vxi. So in principle, you can use any of these equations. But because the acceleration in x direction is 0, so it's a uniform motion in x direction, actually the only useful equation in x direction is going to be the second equation. Why? Take a look at the first equation. If you plug in ax equals 0, what do you get? You just get Vxf equals Vxi. What does this mean? That means the velocity is the same in the initial and final points, which you already know, because you know that in x direction there's no acceleration. What does that mean? That means the velocity is constant. You already know that, right? So the first equation is not going to really help you find anything new. It's just telling you, it's just confirming that velocity is constant in x direction. And then if you plug in the acceleration into the third equation, what do you get? You get Vxf squared equals Vxi squared. It's telling you the same information. The velocity in x direction doesn't change, right? So projectile motion, x direction, because it's a uniform motion, the only useful equation is going to be the second one. So you don't really need to pick an equation, okay? Just always use the second one, okay? That's the only useful equation. Or if you don't remember that, that's fine. Just try the first one. You will see that it doesn't really give you anything. Try the third one, it doesn't give you anything, right? So you don't really need to remember these shortcuts, okay? So if you use the second equation, so let's see, what do I get? So I would get xf equals xi plus Vxi theta t plus acceleration 0, so I get a 0 on the right, the third term. Now if I want, remember what we're doing, we're trying to find Vxi, so I can rearrange this equation, right, if I have all the other numbers. So let's see if I have all the other numbers. Theta t, the problem already tells us, right, this is 9.92 seconds. That's the hang time. So that's going to be the time he travels in x direction from the free through line to the baseline. xf and xi, again, I can always say I set up my coordinate system here, I set my origin here. So at this point, that's x equals 0, y equals 0. If this is x is 0, then xi is going to be 0 for Michael Jordan, right, in this motion. What is xf? Well, the problem says that the distance from the free throw line to the baseline is 19 feet. That's going to be the the xf I plug in, right? If I assume the free throw line is just the x equals 0, it's just the origin. Now you see that I do have all the numbers I need, right? xf, xi, theta t. So if I rearrange this equation, I should be able to find the velocity in x direction. Okay, and then you can't use this number. This is in feet, right? You see that? You have to convert it to meters. Okay, what is the conversion between them? All right, so you're going to convert this to meters, and then you can go ahead and then find the initial velocity. Okay. All right, so now let's see. You can pause the video and then do this algebra. Okay. All right, so first of all, if you convert this, we have done that many times. So the answer I got is 5.79 meters. Okay, now you go ahead and rearrange this equation. What do you get? Vxi equals xf minus xi over theta t. And that's just theta x over theta t. Distance over time equals velocity. That's always true for uniform motion, right? Only for uniform motion. If it's not a uniform, you can't just say velocity equals distance divided by time. You only get the average velocity, right? Now this is going to be equal to 6.29 meters per second. Okay, so that's the first part, the x component of his takeoff velocity. Now the second part. Now I want to find the y component of his takeoff velocity. Y component of his takeoff velocity. That's going to be this guy. So now I'm going to use the same theory in y direction, the same theory, right? So I'm just going to replace all the x's with y's, right? So if I want to find Vy, I think any equation is going to be useful, right? Because the acceleration in y direction is going to be negative 9.8. Then which equation do I use? Okay. Say if I want to try the first one. If I want to try the first one, I would do this. So let's write it down. Plus ay delta t. Okay. So I should rearrange this equation, and then if I have all the numbers I need, I should be able to find the initial velocity. Do I have all the numbers I need? Acceleration, you already know that. You don't need the problem to tell you. Free fall, negative 9.8 is a constant. Delta t, you know that, 0.92, right, for the whole trip. Vy final, you don't know the velocity at this point, right? Again, you need the velocity. It's not zero, okay? We're talking about the projectile motion, so it's right before he lands on the baseline, right? When he lands on the baseline, that's another process. That's a collision. He's getting a force from the floor. That's not free fall. That's not projectile motion anymore. Okay, I'm applying the theory in the projectile motion, so the final point is going to be right before he lands. Okay, so you don't know the velocity he carries when he lands on the baseline. So you don't know that. Okay, but remember, you can always pick any points as your initial or final, and then in a projectile motion, and there's always a very special point you can pick, which is the top. Okay? Why? Because at the top, I know something, okay? Even if the problem doesn't tell me, what is the velocity in y direction at the top? In y direction, it's just a free fall, right? So it's like this. It goes like this. So what is the velocity at the top? 0 in y direction, right? In x direction, it still has this velocity, but in y direction, it's going to be 0. So I know that at this point, okay, we top y component is going to be 0. Okay, so if I say Vy at the top, that's going to be 0. Okay, so this whole trip is still 0.92 seconds, but if I pick this as my final, then I will know the final velocity, okay? So I will have the final velocity and acceleration. And you would say, do I still use 9.92 seconds? No, you don't, right? If I pick this as my final, this as the initial, I should use this time. And this is symmetric, okay? This projectile motion is very special. It is a symmetric projectile motion. The top is at the middle, okay? So the time I plug in for this portion, if I call it data one time, it's going to be half of the time, right? It's going to be this number divided by half, or divided by 2, okay? But this is not always true. A lot of people make this mistake, okay? They always assume the top is the middle of this projectile motion. For example, I can give you another example, right? Something starts from here and lands here. This is the top. Is the top always the middle? No, right? This is not a general conclusion. It's only in the middle when it's a symmetric projectile motion. It starts from the same height and lands at the same height. Okay? So don't make that mistake. This is a mistake a lot of people make, especially on the test. When they see a projectile motion, they always assume the time at the top. The top is the middle. So they just divide the time by 2. You see that? This is not the middle. Okay? The distance, the time is different. In this case, it is. Okay? So now I can go ahead and then plug in this final velocity, the acceleration, and the time, which is half of this. I'm only interested in this half, and then I can find this Vyi. This Vyi is still this initial point, so I can still do that, right? All right, so now you can pause the video, use your calculator, and find this value. Okay? So if you rearrange this equation, Vyi is going to be Vyf minus Ay delta t remember it's going to be 1/2, right? And this is going to be 0 minus negative 9.8. This time is 0.92 seconds divided by 2. Because I'm using the top as the final. What is this number you got? The number I got is 4.51. All right? Okay, once you have these two components, finding the magnitude and direction of his takeoff velocity, that's just vector analysis. That's just trick, okay? So we can now finish the next part, okay? We can finish the next part. So you already have these two components. How do you find the magnitude? X squared plus y squared square root, right? I already found the Vxi, Vyi, square them and square root. What is the magnitude you got? The magnitude I got is this. Okay, so that's the magnitude of his takeoff velocity. What is the direction of his takeoff velocity? Again, usually we use a reference axis and an angle to specify the direction of a vector in physics, right? So in this case, why don't we just pick this angle, the angle between his takeoff velocity and the floor, right? Because that's already a reference axis. So if you want to use this angle is going to be tangent inverse Vyi over Vxi, right? So it's going to be opposite over adjacent, and this side is going to be equal to Vyi divided by Vxi. So what is the angle you got? The angle I got is 35.6 degrees. Okay, you see that's how we estimate Michael Jordan's takeoff velocity from the floor. Okay, we modeled it as a projectile motion, use this theory. Now the last part, how high does he rise in the air? Okay, how high does he rise in the air? That's pretty much the height at the top, right? So if you want to find height at the top, you're still gonna go to y direction, right? You're finding a height. In y direction, you're gonna pick one of these equations, okay? And if you want to find the height at the top, you're gonna still call this final. You still call this final. So you can use either the second equation or the third equation, right? Both of them has YF, and you know all the numbers in these two equations. If you pick this as an initial and final, remember at this point the V final is 0 and time is half, right? Acceleration is negative 9.8. So you can pick either one to find the YF, okay? That's going to be the height of Michael Jordan at the highest point. Okay, now you can pause the video, pick one of the equations, find the height, all right? So say if I pick the second one, what is Yi? That's going to be this. If I call this as my origin, that's going to be 0, right? What is Vyi? Well, we found it here. Now that's Vyi. Now the time, again, you should use this time. So it's going to be 0.92 over 2, okay? And then 1/2 negative 9.8, right? 0.92 divided by 2. Don't forget the square, okay? This Vyi, okay, let me just plug it in. 4.51. Okay? Now you can put all these numbers in your calculator. What do you get? 1.04 meters. Okay? 1 meter, about 1 meter. That's reasonable, okay, for a human. Okay? If you get like 10 meters, well, think about it, right? Can Michael Jordan jump like 10 meters, right? So that's how you, once you have finished the algebra, right? If it's a real life problem, okay, try to make sense of your answer, right? If I get like 10 meters, well, he's not going to jump 10 meters. I know he's Michael Jordan, but he's still a human being, right? 1 meter, okay, that's about right, okay? He jumps 1 meter high, okay? So that's this question. I'm going to stop here for this video.